is the assumption you should have in mind. Okay? So based on this assumption, the Diffie-Hellman key agreement works as follows. So we have Alice and Bob, and they want to exchange a symmetric key over some untrusted thing named Internet. Yeah. And they have all their trusted areas, which are here marked gray. And the first thing everybody does is they exchange some public things. So they agree to some generator and some queue, which is afterwards actually this generator and this queue. So everybody chooses some random number. Alice are A and Bob are B, and everybody calculates this exponentiation, G to the RB modulo Q and Alice to the RA. Afterwards, this X is exchanged, and from this value, everybody can take his randomly chosen number and calculate XB to the RA or XA to the RB. So if we look at these things, what is inside here, so inside this XA, there was the G to the RA, and G to the RA to the RB is the same as G to the RA times RB. So, and the same is on the other side, because inside this one was G to the RB, and G to the RB to the RB is the same as G to the RB times RA. So, with this protocol, both calculated the same value here, which is afterwards the symmetric key. But when you look from the attacker side, who knows everything which is in the white here between, he knows XA, G, and Q, which is the same as here, X, G, and Q, and he knows this value. But what he cannot calculate is the RB and the RA. These two secret values, and these are needed for this last calculation. And based on this assumption, both can agree to some common key over some untrusted area. Okay? So, and we can use this and simplify the key exchange with skipping the key exchange, but replacing the key exchange with some registration phase. So we have some registration, which is the Diffie-Hellman thing. So everybody sends some public key, which is G to the RA, or to some random number, to the server. Of course, here's the modulo. I skipped the modulo again. And afterwards, the server has some registered users. And when we make the poll initialization, we do not send the strings, so Alice and Bob and this will participate, but we send the public keys of these people. So, and afterwards, everybody has the public keys, and maybe you have seen, so that this G is the same for everybody. And of course, the Q is the same for everybody as well. And from this fact, everybody can calculate the common keys from this public key with his secret R. So, okay. Okay. So, and here we look at how this calculation is done. So we have this dashed arrow, which is a logical exchange. So I marked here some logical thing where we want to calculate from this Diffie-Hellman secret, which we just calculated in the way I explained Diffie-Hellman beforewards. And from this one, we want to calculate this vector. So let's look how this can be done. Of course, we have to put this inside some deterministic pseudo-random number generator and get from this what our vector. But as I said at the beginning, this vector is some key for every different time slot. So therefore, I have to include this index into the input of the pseudo-random numerator to avoid getting the same key for several time slots. So, and of course, I have to include some UUID, which is for this poll, because it may occur that we have different polls which have the same time slot, and if I do not include this, we would end up with the same key and these different polls. And something else, which was not at the beginning, I skipped this at the beginning, but I introduced this later. We need some indexing the tables, because we split it up in many tables afterwards, and we need this too. So, and with this pseudo-random number generator, we can generate from our Diffie-Hellman seed all these keys and use this for the calculation later. Okay?
What about the algorithm in the pseudo-random generator? So, is the algorithm public or is it closed?
Of course it's public. So this one,
if you have the inputs, you do not need the key exchange. You can do it on your own if you take the same pseudo-random generator.
No, you do not have this secret. So everything belongs in this secret. Yes. So and this is also a bit a simple product, a simple thing. I've written a more complex thing here where I explained what assumptions we have to put on this pseudo-random number generator, and we have to use some hash function between, which is needed to know who has cheated when we see this -1, which I said. Though I can fetch the slides afterwards if you want to see this. Okay. So then we have some other extensions, because we want to make the scheme a bit more usable, and it may occur that we have started a poll, and after it started already, somebody says, hey, I want to join this poll, I want to join this meeting, I want to also participate. So, and it's a bit of a problem, because we have now here our group, he wants to join, and maybe somebody already voted. So he already sent his vote. So, and this is a problem for this protocol, and we want to have this. So, but we can, it's not a big problem, because what we simply can do is, after he has voted, the key exchange is defined in this way. So we have such a key graph where he has calculated inside his vote a key with Alice, and this is Mallory, for example. So, and when now this person wants to join, he just calculates all the keys with persons who has not voted yet. So, and we have not a full key graph afterwards, but this link is missing from this person to this person. So, and with this extension, we can just use this dynamic joining. So, and another extension may occur. So, think of all these 3 persons have voted, and they see, okay, Alice is on holidays or anywhere else, and she will not give her vote. So, and now we have a problem, because we have unconditional, strong, encrypted votes, and we cannot see what is inside the votes. We have to ask everybody again, let's restart the poll, and there's a problem for this, so what to do now? So, and the good thing is, we can do this without restarting the poll, because everybody, but also we have to ask everybody, but everybody has to agree to this anonymity set reduction, because so beforewards, Mallory would be inside this anonymity set. Ach, schwieriges Wort. And with releasing the keys for her, we can calculate some additional vote, which has a 0 in every time slot. So, and with this additional vote, we can just calculate the sum of everything, and we're ready. So, and now think of not 10 persons and 5 at the beginning, 3 have voted, then 3 are joining. From these 3, 1 doesn't voted, and these things. So we have a really complex key graph, and then afterwards maybe we have to ask 4 persons for their key, and then we can decrypt everything. So maybe such a situation may occur.
If the persons are evil and don't provide the keys?
This is a problem. Of course. So because at the beginning we've configured our anonymity set in this way that we have all the persons inside, and we said, okay, nobody should see what is our vote. So our attacker model is all n-1 people from us has to cooperate to see this. So, and if we have one who does not cooperate, of course,